Good morning. Today we are talking about sequences. Hopefully in class you looked at our formula sheet. We're talking about these bottom two. And I gave you a little introduction to that already. Arithmetic sequences or arithmetic sequences have to do with adding and subtracting, because if you look at our equation right here, it's in the form technically y equals mx plus b, because f of x is a fancy way of saying y. So it's in the form y equals mx plus b. Our pattern, we're doing the same thing over and over again by adding or subtracting. It also helps you here to see that there's a plus. It could be a plus b or a minus b. Then down here are geometric sequences. This is again a fancy way of saying y. Here's an equation that has to do with the geometric sequence. We didn't really learn this, but you can see that these are touching, so you know that means multiply. If we multiplied by a fraction, like 1/4, for example, that's really dividing. You see the division sign there? So this has to do with multiplication or division. So let's first look at arithmetic sequences. It says describe the pattern and then find the seventh term. So for example, this is the first term, second term, third term, fourth term. So we need to find the seventh term out here. So first let's figure out the pattern. From -7 to -3 to 1 to 5. I know I'm going up, and they told me these are arithmetic sequences, meaning I'm adding or subtracting. Think of A for adding, and that'll help you remember those ones. So from here to here, it's kind of hard to tell, so maybe it's easier to tell from 1 to 5. We're going up by 4. 1 plus 4 is 5. If you go back here, -7 plus 4, there's more negatives. 7 minus 4 is 3. It works. -3, if I owe you $3, but I give you 4, you now have one positive dollar, right? You add 4 every time. So if I add 4 again, 5 plus 4 will give us 9. If I add 4 again, 9, 10, 11, 12, 13. So we're continuing our pattern to find the seventh term. And then add 4 again. 13 plus 4 more is 17. So there's our answer. So our pattern, if you want to write it out, our pattern is adding 4. Alright, next, same thing. Describe the pattern and find the seventh term. So here's our first, second, third, and fourth terms. We need to go out to 7. If it helps you to make this a little table so you can see each term, that might be helpful. So from 17 to 13, I'm going down, so I know I must have to subtract. I'm going down by 17 minus what will give you 13? Well, 17 minus 4 would give you 13. 13 minus 4, yep, that's 9. 9 minus 4, yep, that's 5. So let's continue. Minus 4 again. 5 minus 4 is 1. 1 minus 4, we're now in the negatives. 4 minus 1 will give you 3, and there's more negatives, so -3. If I subtract 4 again, a -3 and a -4 is now -7. So our pattern was subtracting 4, and our seventh term was listed there. It's a -7. Next, we're given a formula, and it says, given the explicit formula, or the exact formula, it's right here, for an arithmetic sequence, meaning we're adding or subtracting, find the first two terms and the term named in the problem. So n is what we're going to plug into our equation. So they're telling us n, the little number here, they want us to plug in a 21. So the first two terms, they want us to plug in a 1, a 2, and a 21. So again, if it helps to make a little table, let's do that. So first I'm going to plug in a 1 for the letter n. So I have -10 times n, which is 1, minus 24. So -10 times 1 is still just -10. So same sign, add and keep. 24 plus 10 more gives us 34, and they're all negatives. So that's our first term. Our second term, same thing. Let's plug in for an n, 2. Remember, these are what we're just plugging in for n. So we have -10 times 2, and then minus 24. Well, negative 10 times 2 is negative 20. And then minus 24, same sign, add and keep. So this is a negative now 44. Oops, that's a 4. So then way over here we need to plug in a 21. So we're going to do the same thing, negative 10 times 21 minus 24. So anything times 10, you're just really adding a 0 to. It's 210, because you're multiplying by 10, and it's negative. And then we need to subtract 24. So we have a negative 200. Remember, they're same sign, so add and keep. 10 plus 24 is 34. Negative 234. So there we did exactly what they said. We found the first two terms. Here's our sequence, this, and then we found the 21st term, because that's what they told us to plug in. Let's try the same thing over here. We need to find the first two terms, and now this time it says 12th term. So I'm going to make a little table, so I can plug these in. First I'm going to plug in a 1 for n. So 31 plus 4 times 1. Well, we need to do the order of operations, so we're going to multiply first here. 4 times 1 is 4. So 31 plus 4 is 35. Then I'm going to plug in a 2. 31 plus 4 times 2. Well, 4 times 2 is 8. So I have 31 plus 8 gives me 39. And then we need to plug in way over here a 12. 31 plus 4 times 12. 4 times 12 might be one that you're not quite sure of. That's okay, use your calculator. 4 times 12 is 48. We need to add that 31. So if we add these up, 3 plus 4 is 7, so 79. So this is our list, 35, 39, and then way over there would be 79. Next, we're going to look at geometric sequences having to do with multiplication or division. Describe the pattern, then find the seventh term, just like we did before. So from negative 3 to negative 6, negative 12, negative 24, these numbers, 3, 6, 12, 24, are getting big pretty quick. They're not getting smaller. I mean, they're going more negative, but not in terms of number-wise. 3, 6, 12, 24, they're getting bigger, so I know we're multiplying. Negative 3 times 2 will give me negative 6. Does that work? Negative 6 times 2, yep, that gives me negative 12. 12 times 2 is 24, yep. So our pattern is times 2, multiply by 2. And then we need to find the seventh term. So this is our first term, second term, third term, fourth term. We need to go out to 7. So if I multiply by 2 again, negative 24 times 2, you can use your calculator if you need to. If you're not sure, you can plug in negative 24 times 2, and you get negative 48. Times 2 again. It's already in your calculator, so I'm just going to hit times 2 again. It's negative 96. And then our last one, multiplying by 2 again. One last time, times 2 gives us negative 192. Kind of ran out of room there, but that's our seventh term. Last one like this. Figure out the pattern, and then we'll find the seventh term. From 216 to 72, pretty tough to tell what the pattern is. I have no idea. Still here, pretty tough. But let's just focus on these two. How do you get from 24 to 8? We're getting smaller, so I know we must be dividing. 24 divided by what is 8? Well, 24 divided by 3 is 8, because 8 times 3 is 24. If we go back this way, is 72 divided by 3 going to give me 24? If you're not sure, let's plug it in. Yep, it works. So we know our dividing by 3 pattern works. So now we simply need to find the seventh term. So here's our first, second, third, and fourth term. we're going to plug this in our calculator because I don't know what 8 divided by 3 is. It's not going to be a nice number. 8 divided by 3 gives me 2.6 repeating, so I'm going to just leave it as about 2.6. Since it's already in my calculator, I'm just going to hit divide by 3 again and get 0.8 repeating, so about 0.8. Then one more time, divide by 3 again. We get about 0.29, or if I round it up, 0.3. So I took 0.29 and rounded it up because this second number was greater than 5. Alright, next, given the explicit formula for a geometric sequence, find the first 2 terms and the 8th term. So we're going to find the first term, second term, and the 8th term. So here is our equation. Anything, our n is really what we're plugging in. N is what number? Our n is what number term we have. First term, second term, 8th term. So we're going to plug these in. This whole piece is an exponent. So if we plug in a 1, it says 2 times 3 to the power of 1 minus 1. Well, 1 minus 1 is 0. And if you remember, anything to the power of 0 is 1. So let's test it out. 3 to the power of 0 is 1. So this part here is just 1. So we have 2 times 1, which is 2. Then I'm going to plug in a 2. 2 times, I'm copying this whole equation right here, 3 to the power of 2 minus 1. Well, 2 minus 1 is just 1. So I have 2 times 3 to the power of 1. Well, 3 to the power of 1, 1 time is still just 3. So 2 times 3 is 6. Then we need to plug in an 8 for our final term. We have 2 times 3 to the power of 8. We're plugging in right there. 8 minus 1. So 8 minus 1 is 7. Remember, order of operations, our PEMDAS, says we have to do our parentheses first. We don't have any, so then our exponent. You can't multiply 2 times 3. We need to do our exponent first. So I'm going to plug in 3 to the power of 7. And then I'm going to have to multiply it by 2. So that big number, I'm just going to multiply by 2 and get 4374. 4,374. So that would be our answer. Alright, last one like this. Same thing, find the first 2 terms and the 8th term. So first let's plug in a 1. So we have negative 4 times 2 to the power of 1 minus 1. Well, 1 minus 1 is 0. Just like we did before, anything to the power of 0 right here is just 1. So negative 4 times 1 is negative 4. Then we're going to plug in a 2. Negative 4 times 2 to the power of 2 minus 1. We're plugging in the 2 right there. So we have negative 4 times 2 to the power of 2 minus 1 is 1. So I have 2 1 time is really just 2. So 2 times negative 4 is negative 8. And then we need to plug in an 8. Negative 4 times 2 to the power of 8 minus 1. Now you could plug this whole thing in your calculator. I'm just simplifying it before I might plug it in. So we have 8 minus 1 is 7. So we need to evaluate this piece before we multiply it by 4. So we have 2 to the power of 7. It's not 2 times 7. 2 to the power of 7 is 128. And then times a negative 4 gives me negative 512. There we go. So here is our final answer. Here's our pattern. If we were to list it out, it would be listed out with commas between. So last thing about arithmetic and geometric sequences, the formula that you see on your formula sheet, y equals mx plus b, just tells you that this is a pattern that forms a straight line. Like at our first term, second term, third term, fourth term, fifth term, at our first term we would have a 1. So if we were to plot this, that would be 1, 1. At my second term, I would be up to 4. At my third term, I'd be up to 7. At my fourth term, I'd be up to 11. And this forms a nice straight line. So that's why it's in the form y equals mx plus b. This other pattern, if we were to plug this in, at 1 we're up a half, right? And so on and so forth. I'm not going to do this again. This one is going to form a curve. This is what you'll learn more later. You don't need to know this specifically, but just so if you wanted to know what they look like. Alright, our second part of our lesson is a review of rational and irrational numbers. This is something we talked about the first month of school, so it's been a long time since we've looked at this. So let's talk about our 3 different types of numbers. Well, all numbers are real numbers. We don't have fake or imaginary numbers. So all the numbers that we will deal with until calculus and high school are real. So if anyone ever asks you if a number is real, you will always say, yes, Ms. Calc, all of our numbers are real. Okay? Then the real numbers are divided into 2 categories, rational and irrational. You can't be both. You gotta like pick a category. You gotta go here or you gotta go here. Just like you can't be registered for 2 classes at one time, you can't have math and English at the same time. You gotta have one or the other, okay? So rational numbers are, first, I'm gonna look at this red line, integers, any counting number that you see in your number line. Like, for example, 0, 1, 2, 3, 4, -1, -2, -3. These are our counting numbers that we normally use to talk about round whole numbers, okay? Then we have what are simply called the whole numbers. It has a 0 or an O right in here. They're only the positives. Only the positive counting numbers. So think of these as things you could have a whole, what? If I told you could have a whole pizza, well, 1 whole pizza, or 2 whole pizzas, or 3 whole pizzas, or 4 whole jelly beans, or whatever you want to say. You can't have negative jelly beans. You can't have negative pieces of cake, right? Whatever it is, whole numbers are positives always. So those are integers and whole numbers, and always in whole numbers or counting integers. Then rational numbers also include any fraction or any decimal that does not, that repeats or ends. What I mean by that is the decimal 0.5, it ends. There's nothing after it that we need to worry about. It's just 0.5, 1/2. So fraction or decimal doesn't matter. It's okay. So here, this ends. 2.34, it ends. There's nothing after the 4. This is a rational number. I could owe someone $2.34. It makes sense. Rational numbers always, in my head, make sense in terms of jelly beans, money, whatever it is. Okay. 2 2/3, this one right here. This is a nice fraction. If I wrote it as a decimal, it would be 2.6 repeating. And that's okay. Repeating numbers are okay. Then we have this tiny category that are irrational. These are the odd guys, the weird numbers, okay? They don't end or repeat. And there also are non-perfect squares. So first, numbers that do not end, like pi is 3.14159, and it goes on and on and on, like hundreds and thousands of numbers, okay? There's no end to it. Also numbers that don't repeat. For example, like 12.464789, okay? It's going to go on, and it's not going to repeat. These numbers are also non-perfect squares, meaning it's not a perfect square. Like the square root of 9, if I were to plug that in my calculator, it would give me 3, because 3 times 3 is 9, or 3 squared equals 9. Same with the square root of 16. That's a nice perfect square because it's 4. That's not what I'm talking about here. These ones, if I plug this in my calculator, it's going to give me like 1 point something something something. It's going to go on and on. Square root of 8 is going to give me like 2 point something 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 something. It's not going to end. These are irrational or weird, crazy numbers, okay? So this one looks nice, 35, but I know it's 3 times 5, but that has nothing to do with this. That's not what the square root means. The square root means what number multiplied by itself gives me 3.5. And it would be like 5 point something 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 multiplied by 5 point something 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 will give me 35. So you need to just be careful about your irrational numbers. They're just the weird square roots. Pi, anything that has pi. Fraction that has pi, pi over 2. Still going to be a crazy number. So it says simplify the square root. This is where it might be helpful to look at your formula sheet and list out the perfect squares. I've done that already on my formula sheet, so I'm going to reference that here in a minute. So I want to find the square root of 36. So here's my formula sheet. I listed out the perfect squares, or square roots. The square root of 36 right here is really just 6, because 6 times 6 is 36. So this is just 6. This one I know is going to be a negative number, negative square root of 64. Well, the square root of 64 right here is just 8, because 8 times 8 is 64. Then square root of 81. We really have 9 times 9 is 81. So this is why it's really nice to just list these out on your formula sheet. If we have a square root of a fraction, we can split it up into 2 square roots, like the square root of 4 and the square root of 25. That's a rule we know we can use. We can split it up. So the square root of 4, right here, the square root of 4 is 2 because 2 times 2 is 4. On the bottom, the square root of 25 is 5 because 5 times 5 is 25. So there's our answer, 2 over 5. These next two ask us between which two consecutive integers, these are our counting numbers, is the square root located. So the square root of 41. Well, the square root of 41 is not on our list of perfect squares here, but it's between the square root of 36 and the square root of 49. Those aren't integers, those are square roots. So we need to just simplify it. Well, the square root of 36 is really 6, the square root of 49 is really 7. So it's really between 6 and 7. Same thing here, square root of 136. Oops. Square root of 136, well, that would be way down here. It's between 121 and 144. Which, if you look next to it, is really between, oops, there we go, 11 and 12. Last, I know this one's going to be between two negative numbers, because it's negative. 23 is between, some of you can jump right over here, it's between 4 and 5. If you want to write 16 and 25 first, square root of 16 and the square root of 25, you can do that. Some of you can just jump to the final step. That's okay too. Alright, comparing real numbers. 4 is just 4. Square root of 8 is between which two numbers? Well, square root of 8 is between 2 and 3. So which one is bigger? A number that's like 2 point something or 4? Well, 4 is bigger than 2. So I know that one is greater. Alligator eats the bigger number. Then, which is larger, 3 or square root of 10? Well, square root of 10 would be between 3 and 4. So this is between 3 and 4. So which is greater? 3 or 3 point something? Well, it doesn't matter what the decimal is. 3 point something is greater than just 3 and nothing. Alright, trying to make this last one really quick. It said label the numbers as real, rational, irrational, whole, or integer. Now you can just label them one at a time, or in the past what we did was we made a little table or a chart for us to label our numbers in. Oh, we might need one more there. So we have these numbers, square root of 3, 5.5, negative square root of 16, and 0. And we want to label them as real, rational, I'm going to shorten that, irrational, integer, or whole. So let's just check the boxes for the ones that are true. Remember what I told you about real numbers? I told you, Miss Calc, every number's real, so it doesn't matter. They're all real numbers. Then we need to decide, are they rational or irrational? Remember, it can't be both. You got to pick one or the other. So the square root of 3, well, before here, rational numbers are any number that's a counting number, that's a fraction, or a decimal. All those are good numbers and are perfect squares. Irrational numbers are pi, or any square root that's not a perfect square. So square root of 3, was that one of our perfect squares? Now if you're not sure, look here, was the square root of 3 on this list? No, it was not, so I know that that's not a nice number. It's going to be something weird when I plug it in my calculator. It's not a nice square root, so that's irrational. 5.5, well that's a decimal, it ends. There's nothing after the 5, so that's rational, makes sense. Square root of 16, and it's negative. Well, square root of 16, yep, that's 4. So that's a nice number. So this is really just negative 4. It's a nice rational counting number. 0 is just 0, that's fine. It's not pi and it's not a weird square root. Next are integers. They're all of our counting numbers by ones. So I'm not going to count to a square root of 3. There's no way. I don't count 1, 2, square root of 3. It doesn't work like that, so nope. 5.5, 1, 2, 3, 4, 5, 6, 7. I did not say 5.5, so nope. 1, or I could count negative, 0, negative 1, negative 2, negative 3, negative 4. Oh, there it is. That's an integer. And if I start counting, I can start at 0. 0, 1, 2, 3. That works. Our last piece is simply whole numbers. Are these 0 or positive counting numbers? Can you have a whole cake, a whole jelly bean, a whole fill in the blank? The only ones that are counting numbers that are positives are 0. If I had the number like 7 out here or something, I would also check it for like any other positive counting number. Alright, for the sake of time, I'm going to skip this problem. However, if you would like to know how to order these numbers or want to do this as a challenge, I would suggest doing that. Good luck. Your homework is, right here, sequences on the front side, and then the back side is square roots, rational, irrational numbers. For this part, you need to find which two perfect squares is this between. Then whenever you find that, put the letter, like the letter S, on the line between those two perfect squares. For example, the square root of 30 is, where is it here? Square root of 30 is between 25 and 36. So this, where did we go here? This is between the square root of 25 and the square root of 36. Well, the square root of 25 is really just 5, and the square root of 36 is really just 6. So between 5 and 6 here, I need to put the letter S. So that's what you're going to do for the rest of these. I did the second row for you. I got rid of those problems so you had less to do. And then there's just a couple down here you need to solve. 5 questions at the bottom.